Example 8, we have a baseball that is being tossed upwards by this hand you could barely see. The initial velocity of the baseball is 20 meters per second, and the mass of the baseball is also given. We're asked to determine the amount of work done, and then also determine how high it goes. So let's start off by writing down our given information in this problem. We have the mass of the baseball, which is 0.15 kilograms. We have the initial velocity, or I'll call it v sub 0, is 20 meters per second. And nicely done for us already here. We've decided to make our initial height, y sub 0, I guess, be 0. And that's a good idea because we don't even know how far it is below it. And we're looking for, in the end, part B, our final height. And part A, we're looking for what the work is. Anything else that we need to know? Of course, when the baseball gets to the very top of its path, the maximum displacement upwards, it's going to stop moving. So the final speed here is 0 meters per second. And we're assuming this baseball is being tossed near the surface of the Earth. So the gravitational field strength is 9.8 meters per second squared, or newtons per kilogram. We've been talking a lot about energy bar graphs in class, so why not do it for this problem? So let's start off with establishing our system. I'll draw that circle, and I would assume that the baseball would be part of our system, and of course the Earth. I'm not going to include the hand because we're really going to try to find the work done by that hand. So let's start off with the bar charts, one on the left, one on the right for the initial and the final. Okay, so let's assume that our initial point in time is just as the hand is applying a force onto the baseball. So really, it hasn't gotten any energy yet. And so suddenly we have work, that's my arrow here, being done. And it puts in, let's say, 5 bars of energy. And then the final picture is when the baseball is leaving my hand and I'm not applying a force on here. So then we have a bar here, 5 bars of energy. So this arrow represents the work that is done by the hand, and hence the system gains kinetic energy. So if we were to write our energy statement, we could say in part A that our work done is equal to the change in kinetic energy. The kinetic energy in the final picture here, just as it's leaving its hand. So, and the kinetic energy is given by 1/2 mv squared. And technically, this is our initial velocity, so I'm going to just write that as v sub 0, because our final velocity is actually over here. So now we can just plug in 1/2, that the mass of the object is 0.15 kilograms, and the initial velocity is 20 meters per second squared. So this work would be equal to 30 joules of energy. So this is the amount of work done on the baseball by the hand. So then let's say now the baseball goes up, and it goes up to a certain height. So now let's relabel this as the initially. So we have this, and then our final picture is where the baseball's up here. And when the baseball gets to the very top of its path, then we'll make the assumption that it's not moving, so it has no more kinetic energy, and it's all been converted into gravitational potential energy. Hence, our bars now move over to this side in gravitational potential energy. And we'll make the assumption that it is a frictionless environment so that we don't have to contend with energy lost due to that's dissipated, like say thermal energy. So now I can move on to calculating how high it is by using the conservation energy between this initial position when the ball is leaving the hand and the final position when the ball gets to the very top of its path. So the initial energy is equal to the final energy, or if you look at the initial energy, it's really just kinetic energy, and the final energy is just gravitational potential energy. Okay, I'll just move this over here for a little bit more room. So the kinetic energy formula is given, well, you could actually just substitute in here if you want. But let me just put in the actual formula. You'll see something interesting happen. If you put in 1/2 mv initial squared, and then the final gravitational energy is just mg, and then the y final, Remember that there's no initial y, so there's no gravitational energy, and there's no final kinetic energy because it's not moving at all. You'll see what I find interesting here is the mass cancels out. So it really wouldn't matter. You don't really need to know the mass of the object at all. It will cancel out. So to find out our final y height, it would be v0 squared divided by 2 times g. And the initial speed is 20 squared divided by 2 times 9.8. And this gets you an answer of 20.4 meters. Okay, that's it with this problem.